Okay, next comes associativity. Again, I'm just plowing right through this. Please get on Discord and ask me questions. So, beforehand we talked about, let's see, block cache sizes and write through. One thing I didn't mention, and I really should point out to the security people here, is notice that in a block size, if our block size is huge, and we're going to bring in 128 bytes, there's a security issue here. Because what if in our operating system, the end of our program happens to be right next to where the secret key is being stored? Well, if that's the case, then the secret key would also be brought into the cache of a process that probably shouldn't have access to that secret key. Now, most of these systems, and by most I mean all of our systems, do have memory protection schemes in order to prevent a process from reading from that section of cache. But the fact that it's in the cache actually will lend itself to another security attack, which we will get to later in this course. And actually, it's what one of the basis for how Meltdown comes down. But we will get to that closer to the end. But today we need to move on to something called associativity. And associativity is another cache optimization in order to reduce the tag size, which helps us in doing lookups. Again, it's hard for us to see why this is important. The EE guy, any electrical engineer can see this because the CAM is very big, so anything we can do to reduce the CAM tag lookup will be very helpful, and associativity helps us a lot. All right. So we've done fully associative cache because that means any piece of memory can go to any cache line. So associativity is going to limit the number of cache lines a piece of memory can go to. And so fully associative, one piece of memory can go to any cache line. Direct map means that each piece of memory can only go to one cache line. And let's go ahead and do an example here. So in this case, we're going to have a direct map. And what's going on here is notice that beforehand our tag was the tag and what the set index bits were, and then we just had a block offset which represented how far down. We're now going to change this up again by having 4 cache lines, and since we're having a direct map cache, we need to have 2 bits that signify which cache line it goes to, and then a tag bit to signify which tag line is going to be in there. Alright, again, this is confusing, but direct map, remember all data can only go to one cache line, and so I've color coded it here for you. And blue, and then magenta? Sure. And I'll call this purple? Yeah, let's call it purple. And notice that our set tells us which set we're allowed to go to. Since it's direct map, each set only has one cache line. Notice that LRU no longer makes sense because since each line can only go to one, or each byte of memory can only go to one cache line, everything's the LRU. I'll show you in a moment. So notice 1 can only go here. And notice, by the way, that we only have 2 cache lines, so the set is 1 bit. So this address was 0001. You may have to think about that for a moment. Notice that back here, 00, in this case we had 2 bits, but it can be just 1 bit, 0, and then 1. Let's do another example, 5. Well, 5 is 0, 1, and then 1 again, followed by a 1. So it can only go to this cache line down here. Or did I say that wrong? 0. Oh, I'm sorry, you were right. I was thinking 7. 0, 1, 0, 1. So yes, it can only go to the top cache line. Alright, 2, so that can go on the bottom because it's 0, 0, 1, 0. 7, well 7 is going to be 0, 1, 1, 1, so that 1 right in the middle can go right here, so it's going to overwrite this guy. We're going to have to go ahead and store it back out to memory and read it. And then we're going to load 4. What's 4? 0, 1, 0, 0. So that's third bit was a 0 up here, and that tag's already in there, so it's the 71. Namely, that 4 was brought in when we brought in the 5. So let's see. Show the breakdown of the address for this configuration. Oh boy. I really wish we had the board today. I'll tell you how to do this. So we have a 32-bit address. That means that this entire address must be 32 bits. We have a 16K cache. We'll get to that in a moment. Direct map and 32-byte blocks. So if it's 32-byte blocks, that's the easy one, because how many bits are required to represent 32 bytes? Well, 2 to the 5th is 32, so you need 5 bits. The question is, what's the set index? Well, it's direct map, so that means that each data or datum or piece of data can only go to one cache line. All right, great. Well, how many cache lines are there? Well, it's a 16 kilobyte cache and 32 blocks, so we need to go ahead and divide the two. How do we divide that? Well, what's 16K? Well, that is what? 1K is 2 to the 10th, 11K is, 2 to the 11th is 2K, 2 to the 12th is 4K, 2 to the 13th is 8K, and 2 to the 14th is 16K. So that's 2 to the 14th, this is 2 to the 5th. So 2 to the 14th divided by 2 to the 5th is 2 to the 9th, which means that you have 9 bits for your set index. So that's 9 bits here. Block offset's 5, so that means this is 13. So 32 minus 13 would be the tag of, should be 19 should be left over. Ooh, cache. Alright, class problem 5. Notice that our cache line is now 4 bits long. We have 2 cache lines, so it's one set, and then a tag of 1. So let's go ahead and load in from 3. That would be, excuse me a moment, that would be 0, 0, 0, 1, 1. So the tag is 0, that first bit, and then comes your set, which would be 0, and then 1, 1, which would be this guy right here. So all this data would go right here. Next comes 12. 12 is 1, 1, 0, 0. So that first one is your tag. The next one is the set, so it's going to be this one. And then 0, 0 here, so we're bringing in this element right down here. Bringing the 15. Well, the 15 was brought in when we brought in the 12, so that's a hit. Then we load out to the 4. The 4 is a miss, because the 3 only went up to here. So what's the 4? The 4 is 0, 1, 0, 0, so we're going to have to evict this, which means we need to write it back because we just stored it. So we write it out, then we bring in 4 to 7 down here, and then we're going to add 9. 9 is 1, 0, 0, 1, and that'll be this guy up here. That is not what's being stored, so we're going to have to go ahead and we just evict it. We don't have to write it back because nothing's dirty. Bring in those 9s and then service it. You may need to do this by hand. Okay, so we've talked about basically the two extremes. The direct map is where only every piece of data can only go to one cache line. Fully associative is where a piece of data can go to any cache line. Well, set associative basically says how many sets can a cache line go to. All right. So, in this example, the set associative is 2 when we have 4 cache lines, meaning that each set has a total of 2 cache lines. Yeah, I know this part's confusing. Again, there's 4 cache lines. We're two-way set associative, so that means that each data can go to 2 cache lines. So we're going to have a set. Each set will have 2 cache lines. So here's one set here and another set here. Notice that that gives us only one set because there's only 2 sets in total. Let's do a quick example. Oh, by the way, this is the way the book displays it. I think it's a little confusing. I think this is a little easier to see, but just knows that the book style is this way. All right, here we go. So first one, memory reference 0. That would be 0001. So we'll bring it up here. Notice that the LRU is part of the set now, because each set you can think of as its own little mini cache. And so your set is your address will say which set that the cache line can go to, and then you must do the LRU with inside of it. So we go to 5. brings it down here. Oh, again, sorry, skipped a bit. 5 is 0, 1, 0, 1, and so that next to last bit is the set, which was a 0, so it would be up here. Next comes 7, which is 0, 1, 1, 1, so it's going to come down here. Next comes 4, which is 0, 1, 0, 0, so that next to last bit is a 0. It means we're going to have to jump up here. Luckily, it was brought in with the 5, so we just overwrite it right there. We're going to load from 0. Luckily, 0, 0, 0 was brought in when we brought in the 1, so that's also another hit. And then next, we're going to load in 8. Well, the 8 is 1, 0, 0, 0. So that would be the setup here, which means, and it's not in either of these cache lines, so we're going to have to go and write this one back and then bring in the 8. Okay, you may need to watch that a bit. Keep in mind that the associativity is how many cache lines a data can go to. So we're on a two-way associative. I never said it up here, but that means each of these data can go to one of 2 cache lines because it's two-way set associative. Since we have 4 cache lines, and we want to 4 cache lines, and there are 2 lines it can go to, there are now 2 sets. All right, let's go ahead and break down here. Whoops. Again, 32-bit address. That's how many bits we need. 64-byte blocks. Well, that's easy. That's 2 to the 6. So the byte offset is 6. How many cache lines is that? Well, 16K is 2 to the 14th. Now we have 2 to the 6th. When you divide those out, that's 2 to the 8th. So there's 2 to the 8 cache lines. But it's 4-way set associative, which means that each data can go to one of 4. So it's 2 to the 8 divided by 2 to the 2nd, which is what, 2 to the 6. So there's going to be 6 bits to your set. Then you have 6, so it's 6 plus 6, that's 12. 32 minus 12 will then be 20 for the tag. Whew! Fully associative. All right, here we go. Well, fully associative means there are no set bits, so that actually makes this way easier. 64-byte blocks, again that's 2 to the 6 for the byte blocks. Everything else is the tag, so 32 minus 6 is 26. Alright, cache problem again. Two-way set associative, no write allocate or write back. So two-way set associative means that each data can go to one of 2 cache lines. So we're going to have these 2 cache lines the first set, these 2 cache lines are the next set. So we're first going to bring in 11. 11 is 1, 0, 1, 1. So since that next to last bit was a 1, we'll bring it down here. We'll put a 10 here and 11 there. Yay. So then 2 comes in, that's 0, 0, 1, 0. That next to last bit is a 1. So we'll bring the 2 here and the 3 down here. We stored a 12. Well, 12 is not, well, hold on. 12 is 1, 1, 0, 0. So it's not in the cache, so we'll bring it up here. 3 is 0, 0, 1, 1. Not in the cache, so we'll bring it right here. Ooh, that's a lot of things to keep in memory. Now we're going to load that 7, which is 0, 1, 1, 1. That is not in the cache. Its next last bit's a 1, so it's going to come down here, and it's going to overwrite whatever was on top here. Yeek. Which I think was the 11. And that would make this 10 a miss when it comes in here and needs to evict this one down here. Wow, that's all misses. Okay. You probably need to watch all that slowly again. But the cache is too small to hold all the data. Maybe I should also remind me on Discord if I forget to post the video from the last time I taught this in class. That will probably help a lot. The cache is too small to hold all the data. Basically, what we're asking on this slide is what are the reasons that a cache miss? These are known as the 3 C's for a cache miss, or actually there's 3 common C's. There's a couple more reasons, but we're not going to get to those in this class. First one is the cache is too small to hold data. That's a capacity miss. AKA, let's say you're trying to sort 1,000,000 items, but your cache can only hold 1,000. You need to build a bigger cache. The first reference to an address is usually a miss. You do that, that's called a compulsory miss. You reduce this by increasing the block size in order to capture more hits when you reference that data, aka try and capitalize on spatial locality. Replaced it from a busy set, aka let's say your associativity was too low or you have a direct map and it just keeps overriding the same cache line. That's called a conflict miss. You had another item that was available in the cache, but it didn't go to it because of your associativity of the cache. That's called a conflict. You reduce it by increasing your associativity so that you can utilize more of the cache. Hopefully you can see that these are all at odds with each other or would slow down your cache. For example, capacity miss, the bigger you make your cache, the slower it's going to be. That's why you have an L2 cache. While it's slower, it's also bigger. An L1 cache, which is smaller. Compulsory miss block size. If you increase the block size too much, then what's going to happen is you're going to start evicting data that you're going to need, and you'll stop capitalizing on spatial locality when temporal locality would be more advantageous. And a conflict miss, you can only increase your associativity so much before the laws of EE kick in, and it will slow down your cache because of the wide tag lookups that you must do. All right. Also, what about instructions? Notice we've only talked about data, but can you cache instructions? Well, it turns out that caching instructions is actually very advantageous and very helpful because cache instructions generally follow one after another, after another, after another, after another. You may jump back up again, but then you go back one to another, to another, to another. So all processors do have an instruction cache, and they usually have a very long block size and usually some type of prefetching mechanism in order to make sure that it gets to the next instruction. So you replace instruction memory with what we call an I cache, instruction cache, and data memory with what we call a D cache. So memory access now has variable latency, and both caches may miss at the same time, and you must actually add hardware that if there's a miss, you gotta stall your pipeline until the instruction comes in. So this is the MIPS 32. This was the old architecture that we forgot to talk about, that I didn't replace this, but the instruction cache would be here and the data cache would be here. Notice what's not shown is that there is going to be a line from the instruction cache to main memory, as well from data cache over to main memory as well. Alright, and here's the hierarchy again. SRAM's has the highest cost, lowest latency, aka it's the fastest, worst or high access because of smaller, main memories in the middle, and disk storage is the slowest. Even SSDs are still slow compared to DRAM and SRAM. Alright, we're going to stop here because next we're going to talk about a problem with, we want to have, well, DRAM is not too expensive to have many gigabytes, but it's too expensive to have terabytes nowadays. We're going to get to how we work around that in today's world. But I'm going to pause here because we've definitely gone through